To illustrate two more charts that we have, the X-bar chart and the R chart, we're going to go back to the sample data. You can do this by going into SAS and just selecting the Help, Sample Data, Control Charts, and we're going to choose the diameter data set. And as you can see, we have different diameters labeled for different processes. Actually, it's the same process for this machine through different phases, and we're going to build a chart to see what variations we have in our diameter, and we want to see if we're staying in control or not, and we'll talk a little bit more about what that means later. So it will take you to a very simple control chart builder, and then it will help you produce these different charts that we have. And as you can see up top, we have the X-bar chart and the R chart, the range chart, and the average chart, as they're called. So for the average chart, or the X-bar chart, it's going to take different samples of these parts that we're going to produce. Let's say they're like a screw or something, and we want to measure the diameter, and it's going to plot it on a point, and we want to see how close to this center line, this mean, we can get. And the way we do that is we set a boundary. We have the upper control limit and the lower control limit, and these are set within our specifications. So if it's out of control, it might not have hit our specifications yet, but we don't want it to be above this upper control limit line or below this lower control limit line. And it also has these kind of markers on it, so you can see these 2 points are marked with a box. This can be changed and set to whatever you want your chart to look like, but that's obviously showing us that this is out of control. It's showing us some warning signs down here with these X's and just different things, and you can look at this data and see if you're out of control or in control. Now the range chart, it's going to take samples as well, but you want to see what the variation is like in these samples. And these are two just very helpful charts that are going to show if our processes are out of control or in control, and we can look at those warning signs and correct, and hopefully we can keep it within those specifications and well within control.
Hi, this is Joey Gugliardi, and I'm going to be talking about the UWMA and EWMA charts. As you can see, this is the data that we used. It has various samples, 1 through 100, and we have 5 subsamples or trials for each. We have gaps for each one. I think this is a unit of time, and the status, whether it was A or B. So the UWMA chart. So this is what it stands for is the Uniformly Weighted Moving Average. This is a type of control chart that is used to monitor small shifts in the process mean, and it uses the average number of consecutive observations. So this chart we have in particular is plotting the moving average of subgroup means, because we broke it up into subgroups. So given a series of observations and a fixed subset size, the first element, so if we took just the first element of this chart, it is calculated by taking the average of the initial data. But then to get the next number, we exclude the first initial number of the series and include the next number of the series, and we continue to do this throughout the entire chart. This is also a control chart, so there's an upper and lower control limit, and it typically uses about 3 sigma for that. Now the EWMA chart's a little bit different. It's exponentially weighted moving average. It also is used to monitor small shifts in the process mean, and so it weights observations in geometrically decreasing order, so that the most recent observations contribute highly while the oldest observations contribute very little. This UWMA chart is plotting the exponentially weighted, as opposed to just the moving average, the exponentially weighted moving average of subgroup means. So there's the way that you calculate this, there's an equation for that. It's computed by taking 1 minus the weight times the previous EWMA plus the weight times the current observation. And this is modified by also shifting forward, just as we did for the last one, repeating this calculation across the entire series. Thanks for listening.
Pareto plots are like the ranked order histograms that include cumulative percentage line. For this presentation, we chose failure size example from the sample data. In JMP, we go to Help, we choose Sample Data, we control Charts, and then we use failure size example. In this table, we have the process columns, which are process A and process B. We have the day, causes, count, and iProcess columns. When we run the rate Pareto plot, we get the following analysis: the count on the y-axis and the causes on the x-axis. We have a plot for process A and another plot for process B. And then in the following picture, we see the unit rates for process A and process B. We see the rate for each process and the rate according to the lower and upper confidence interval. In the plot, the taller bars, which present frequency on the chart, help us in analyzing the problems that need more attention. And in here, we get the following graph and analysis if we run the DPU Pareto plot. We also have the count and causes on the axis for process A and for process B. The frequency bars, which are these bars, show us which causes impact our analysis or our count the most. We can get the same analysis results if we run the same experiment using other tools like FitY/X or the DOE.
Hi, this is Jim, and I'll be briefly analyzing each chart and talking about when the chart is out of control and what that tells about the process of product. So here we have sample data of diameter, and we're going to look at the X bar and R chart. What it's telling us is the averages and ranges of diameter over a certain time, over the process time. And looking at both charts, there are some sudden moves and two plots that are out of control, but the overall plots are all within the lower and upper control limits, and the overall plots are decreasing, which means the process of product is showing constancy in making their product. The X bar and R chart shows the out of control when too much plots are out of the lower and upper control limits, or when the plots shows increasing movement, which means the process of product is showing inconstancy in making their product. Next, we're gonna look at uniformly weighted moving average and exponentially weighted moving average. And here we have data collected of gap of clips. So what uniformly weighted moving average shows us is the average of gap of clips over a certain amount of sample. And here we have a sample size of 3. So each averages of plot. Each plot shows the subgroup, 3 subgroups of each data set. And overall plots, looking at the data, the overall plots are within upper and lower control limits, and the overall movement is decreasing. EWMA is also showing the average of gap of clip, but for this case, all the previous subgroups are accumulated, so each plot shows the accumulated average of the gaps of the clip. And again, most or all of the plots are within lower and upper control limits, and also the movement of the plots is decreasing. When UWMA and EWMA are out of control is when too many plots are out of upper control limit and lower control limit. Next we have Pareto plot, and it can be a referential chart for the previous 2 plots, because it's simply showing where the most defects are occurring. Here we have a failure size example data, and here is the Pareto plot. So looking at both process A and B, seems like the size is the main factor of the defect, and for A, it's about 40% that is of all defects, and for process B, the size defect is about 60% of all defect. Also for process A, contamination is also a main cause of a defect, and it's about 30%. Thank you.